Today we are going to learn about mastering Atom Optimizer in TensorFlow. We'll explore how to implement and fine-tune the Atom Optimizer to enhance your model performance efficiently.
Hello and welcome to our session on mastering the Atom Optimizer in TensorFlow. ADAM, which stands for Adaptive Moment Estimation, is a powerful optimization algorithm widely used in training deep learning models. Its popularity stems from its ability to adapt the learning rate during training, making it highly efficient for complex models. Today, we'll dive into the workings of the Atom Optimizer, learn how to implement it in TensorFlow, compare it with other optimizers, and understand how to fine-tune its parameters for optimal performance. By the end, you'll have a comprehensive understanding of how to leverage ADAM to enhance your machine learning projects. The Atom Optimizer is a method that computes adaptive learning rates for each parameter. ADAM combines the advantages of two other extensions of stochastic gradient descent, AdaGrad and RMSProp. The core idea is to maintain both first and second moment estimates of the gradients, which helps in dynamically adjusting the learning rate for each parameter. This adaptability makes ADAM particularly effective for large datasets and high-dimensional parameter spaces. The optimizer is designed to work well in practice with little configuration or hyperparameter tuning, making it a favorite among practitioners. It is commonly used in various deep learning architectures, such as convolutional neural networks, CNNs, and recurrent neural networks, RNNs, due to its robust performance in optimizing non-convex problems. The balance it strikes between computational efficiency and precision in updating weights contributes to its widespread adoption. In the realm of optimization algorithms, ADAM stands out due to its adaptive learning rate, which is not a feature of traditional optimizers like stochastic gradient descent, SGD. While SGD updates the weights using a single learning rate, ADAM adjusts the learning rate for each parameter based on estimates of lower order moments. This allows ADAM to perform well on sparse data and noisy gradients. When compared to AdaGrad and RMSProp, ADAM incorporates the benefits of both. AdaGrad is effective for sparse data, adjusting the learning rate based on the frequency of updates, but can result in a diminishing learning rate over time. RMSProp improves on this by normalizing the gradients. ADAM takes it a step further by computing both the mean and the uncentered variance of the gradients. When choosing the right optimizer, one must consider the nature of the problem, computational resources, and the desired speed of convergence. ADAM's ability to handle non-stationary objectives and noisy data makes it a versatile choice, but practitioners should be aware of its computational overhead compared to simpler methods like SGD.
The learning rate is a critical hyperparameter that dictates the size of the steps taken towards the minimum of the loss function. In the Atom Optimizer, the default learning rate is often set at 0.001, but this is not a one-size-fits-all solution. Adjusting the learning rate can significantly impact the convergence speed and final accuracy of your model. Implementing a decay schedule can help reduce the learning rate during training, allowing the optimizer to fine-tune the weights more precisely as it approaches convergence. A common strategy is to start with a higher learning rate and gradually decrease it, which can help the model escape local minima and converge faster. However, setting these parameters requires experimentation and a good understanding of the problem domain. It's advisable to monitor the training process and adjust the learning rate schedule based on the model's performance on the validation set. Practitioners often use techniques like learning rate annealing or cyclical learning rates to optimize this process further.
Beta 1 and Beta 2 are crucial hyperparameters in the Atom Optimizer that control the exponential decay rates for the moment estimates. Specifically, Beta 1 is the decay rate for the moving average of the gradient, while Beta 2 is for the moving average of the squared gradient. The default values for these parameters are 0.9 and 0.999, respectively, which work well in many settings. Beta 1 helps in smoothing the gradient updates, making the optimizer less sensitive to noisy data and leading to more stable convergence. Beta 2, on the other hand, ensures that the learning rate is adjusted based on the variance of the gradients, preventing the optimizer from being too aggressive. However, these default values may not be optimal for all problems. Fine-tuning Beta 1 and Beta 2 can be necessary for specific tasks, especially when dealing with different types of data or architectures. Practitioners need to experiment with these parameters to find the right balance between speed and stability, ensuring efficient convergence without sacrificing model accuracy.
Implementing the Atom Optimizer in TensorFlow is straightforward and involves a few simple steps. First, ensure that your TensorFlow environment is properly set up. This involves installing the TensorFlow library and setting up your development environment. Once that's done, you can define the Atom Optimizer as part of your model training process. In TensorFlow, the Atom Optimizer is defined using the tf.keras.optimizers.atom class, where you can specify the learning rate, Beta 1, and Beta 2 parameters among others. Integrating Atom into your model involves specifying it as the optimizer when compiling your model. You can adjust the hyperparameters based on the specific needs of your project, using validation performance as a guide. It's crucial to monitor the training process closely, watching for signs of overfitting or underfitting, which may require further adjustments to the learning rate or decay schedule. TensorFlow also provides tools for visualizing the training process, which can be invaluable in fine-tuning your model and ensuring optimal performance with the Atom Optimizer. While the Atom Optimizer is robust and versatile, there are common pitfalls that practitioners should be aware of. One major issue is overfitting, which can occur if the default parameters are not suitable for your specific dataset or model architecture. This is why it's crucial to experiment with different hyperparameter settings and not rely solely on default values. Another common mistake is neglecting data preprocessing, which can lead to poor performance regardless of the optimizer used. Properly cleaning and normalizing your data can significantly impact the effectiveness of the Atom Optimizer. Inadequate hyperparameter tuning is another pitfall. It's important to take the time to experiment with different configurations, using techniques like grid search or random search, to find the optimal settings for your specific problem. Monitoring validation performance is essential, as it provides insights into how well your model is generalizing. If performance on the validation set starts to degrade, it may be necessary to adjust your learning rate or other parameters. Finally, always be prepared to adapt your approach based on the specifics of the problem you're tackling. Each project may require unique considerations that go beyond general best practices.
Let's walk through a practical example of training a neural network using the Atom Optimizer in TensorFlow. We'll start by selecting an appropriate dataset, such as the MIS dataset for digit classification, and proceed with data preprocessing. This involves normalizing the pixel values to ensure that the neural network can learn effectively. Next, we define our model architecture, which might consist of several convolutional and dense layers. Once the model is set up, we compile it with the Atom Optimizer, specifying the learning rate and other hyperparameters. During training, we closely monitor the loss and accuracy metrics on both the training and validation datasets. This helps us identify any issues with overfitting or underfitting that might require adjustments to our hyperparameters. After training, we evaluate the model's performance on a test set to ensure that it has generalized well. This practical example highlights the importance of each step, from dataset preparation to hyperparameter tuning, in successfully training a neural network with the Atom Optimizer. Fine-tuning the Atom Optimizer's performance involves a combination of strategies and techniques. Experimenting with different learning rates is a fundamental approach. Sometimes, starting with a high learning rate and then decreasing it can yield better results than sticking to a constant value. Implementing learning rate schedules, such as exponential decay or step decay, can help maintain a balance between rapid initial learning and precise convergence. Monitoring the magnitudes of gradients during training provides insights into whether the optimizer is making effective updates. If gradients are too large, it might indicate the need for a smaller learning rate. Regularization techniques, such as dropout or L2 regularization, can help prevent overfitting, especially when dealing with complex models. Finally, leveraging early stopping is a practical approach to halt training once the model's performance on the validation set stops improving, preventing unnecessary computation and potential overfitting. These tips can help you fine-tune the Atom Optimizer's performance, ensuring that your model trains effectively and efficiently.
In conclusion, mastering the Atom Optimizer in TensorFlow is a valuable skill for enhancing your deep learning projects. We've explored the strengths of Atom, such as its adaptive learning rate and ability to handle noisy data. Understanding and fine-tuning hyperparameters like learning rate, beta 1, and beta 2 are crucial for achieving optimal results. Implementing Atom in TensorFlow requires attention to detail, from setting up your environment to monitoring training performance. By avoiding common pitfalls and continuously experimenting with different strategies, you can leverage Atom's capabilities to their fullest. Remember, continuous learning and adaptation are key to success in the ever-evolving field of machine learning. Thank you for joining us, and happy optimizing.